Hello friends, welcome back to my YouTube channel. In the 12th part of my discussion on molecular diffusion, I will be discussing about diffusion coefficients for gases. So in this discussion, I will let you know about various equations that are available in the literature to predict diffusion coefficients for gases. And henceforth I will be discussing diffusion, how to predict diffusion coefficients in gases, and then I will discuss how to predict them in liquids. So in this video lecture we will know about various equations that are available in the literature to predict diffusion coefficients in gases. So let us begin the discussion. First of all, we will understand what is a diffusion coefficient. So for that, we need to know what is Fick's first law of molecular diffusion. I have discussed it in one of my earlier videos. I am giving link to the entire playlist that has all my video lectures on molecular diffusion through fluids. The link is available in the description section. So Fick's first law of molecular diffusion. In order to understand the law, we will consider a mixture of two gases, gas A and gas B, a mixture of gases A and B. So we are considering a binary gas mixture. So in this binary gas mixture, for molecular diffusion of A in the Z direction, if A is diffusing, if there is molecular diffusion of A in the Z direction, then according to this law, Ja is directly proportional to dabba C A by dabba Z, because we are writing the law only for the Z direction. Diffusion may be taking place in X and Y direction. So that's why we need to use a partial derivative. So Ja, I will shortly tell you what is Ja. So Ja is directly proportional to dCA by dZ. Molar flux, Ja is molar flux. Molar flux of A is directly proportional to the concentration gradient in the Z direction. So this law describes molecular diffusion. This equation describes molecular equation in the Z direction. If you remove the proportionality, we will have to introduce a constant, and the constant is dAB. So in that case, the equation will be Ja is equal to minus dAB into dabba Ca by dabba Z. And if you neglect molecular diffusion in X and Y directions, that means if we assume that there is diffusion only in the Z direction, then we can replace this partial derivative with total derivative. So in that case, the law will be written in this way. Ja is equal to minus dAB into dCA by dZ. Now you have the total derivative. Now in this equation, Ja is the molar flux of A relative to the molar velocity of B. I have discussed about it in details in my discussion on Fick's first law of molecular diffusion. You please watch that video. So Ja in this case is molar flux of A relative to the molar velocity of B. dAB is the proportionality constant, and it is nothing but the diffusion coefficient, or simply diffusivity of A in B. So dAB is diffusivity or diffusion coefficient of A in B, and dCA by dZ is the concentration gradient in the Z direction. So Fick's first law of molecular diffusion states that molar flux of A in a given direction is directly proportional to the concentration gradient in that direction. And why there is a negative sign in the equation? The negative sign indicates that molecular diffusion occurs from a place of high concentration to a place of low concentration. So basically now we know what is the mathematical equation for Fick's first law of molecular diffusion. Ja is equal to minus dAB dCA by dZ. So this gives molar flux of A relative to the molar velocity of B in the Z direction. The negative sign in the equation indicates that molecular diffusion occurs from a place of high concentration to a place of low concentration. So I hope the law is clear to you. If you have any doubts, you please watch my video on Fick's first law of molecular diffusion. The link to the entire playlist is available in the description section. Let us move ahead. So Fick's first law, continuing with the law, you have this equation, the mathematical equation, JA is equal to minus DAB dCA by dZ. Now what we will do, we will consider only magnitudes. That means we will, for time being, we will ignore the negative sign. That is, we will just consider the magnitudes. So in that way, JA will be equal to DAB into dCA by dZ. Why I am doing this? Because I will be getting an equation for DAB. So from this, I can write equation for DAB as DAB is equal to JA upon dCA by dZ. That means according to this equation, DAB is equal to JA if the denominator is 1. That is dCA by dZ. If it is 1, then DAB will be equal to JA. So you can, from this equation, you can define the diffusion coefficient as, the diffusion coefficient is the ratio of the molar flux to the concentration gradient in the given direction. So it is the ratio of molar flux of A to the concentration gradient of A in the given direction. So, and as I said, if dCA by dZ is 1, that means DAB will be equal to JA. So in that case, if this denominator is equal to 1, then simply DAB will be equal to JA. So by that way, we can understand diffusion coefficient as it is the molar flux due to unit concentration gradient in the given direction. So you can understand in this way as well. Diffusion coefficient, it is the ratio of the molar flux to the concentration gradient in the given direction. Or you can understand it in this way. It is the molar flux that will be resulting due to unit concentration gradient in the given direction. So I hope now you know what is a diffusion coefficient. Let us move ahead. Now let us get the dimensions. So we got equation for DAB. DAB is JA upon dCA by dZ. So if I use the units, so dimensions for DAB will be equal to dimensions for JA. What are the dimensions for JA? The unit for molar flux is, it is kilomole per meter square per second. That is, the dimensions will be kilomole L raised to minus 2 T raised to minus 1. And the dimensions for the concentration gradient, for Ca, it will be kilomole into L raised to minus 3. And for the direction or distance, the dimension is L. So if you simplify this, it will be DAB will be equal to kilomole L raised to minus 2 T raised to minus 1 divided by, I have simplified in the denominator, so it will be kilomole L raised to minus 4. If this L goes over here, it will be L raised to minus 1. In that case, we will be having L raised to minus 4. So in the next step, kilomole will get cancelled. So we are left with dimensions for DAB is equal to L square into T raised to minus 1. So these are the dimensions for the diffusion coefficients. Then units, accordingly, in different system of units, you will have different units. For example, in SI system of units, the units for diffusion coefficient will be meter square per second. In CGS system, it will be centimeter square per second. And in FPS system, it will be feet square per second. And mostly in literature, the values of diffusion coefficient, they are reported in centimeter square per second. So now you know various units for the diffusion coefficients in various systems of units. Then diffusion coefficient, if you have to talk more about it, what is it actually? It is a measure of the mobility of substance by molecular diffusion. How fast or how effective is the mobility of a substance by molecular diffusion? It is measured in terms of its diffusion coefficient. So that's why we are saying diffusion coefficient. It is a measure of the mobility of a substance by molecular diffusion. And then it depends on various parameters. It depends on the nature of the component. So in this case, in the mixture of A and B, it will depend on the nature of A and nature of B. Then it will also depend on temperature. It will depend on pressure. So over here, we have understood that the dimensions for diffusion coefficients are L raised to 2, T raised to -1. Then units in SI system, meter square per second, in CGS system, centimeter square per second, in FPS system, feet square per second, and mostly in literature, the values of diffusion coefficients, they are reported in centimeter square per second. So diffusion coefficient, it is a measure of the mobility of a substance by molecular diffusion, and it depends on factors like nature of the component, it depends on temperature, and it also depends on pressure. You'll shortly know how they are dependent on these factors. Let us move ahead. Now let us talk about various equations that are available in the literature for estimating diffusion coefficients for gases. Before that, we need to understand that there are two ways in which you can estimate diffusion coefficients. So diffusion coefficients for gases, they can be estimated in two ways. So one is you can do it experimentally, you carry out some experiments, and then by appropriately representing the data, you can get diffusion coefficients. So one way is to get diffusion coefficients experimentally, and the other way is you can also estimate those diffusion coefficients by using equations that are proposed by various authors. And in this discussion, we are going to know about these equations. We are going to know few equations that can be used for determining diffusion coefficients. So wherever it is possible to carry out experiments and collect the experimental data, you can easily find diffusion coefficients experimentally. But in the absence of experimental data, or where it is not possible to carry out experiments, then you can use equations that are available in the literature. Experimental values, if you have to talk about them, they are highly accurate because they are determined experimentally. But those values, they may not be available in every situation. It may not be possible to carry out experiments in all situations. Even though they are highly accurate, but in absence of the experimental data, we will have to depend on the equations that are proposed in the literature. So theoretical values, which are calculated by using these equations, theoretical values, they are estimated by using equations that are proposed in the literature. And these equations, they are based on the kinetic theory of gases. For gases, you have the kinetic theory, and from the kinetic theory, different authors have proposed equations for calculating diffusion coefficients in gases. So since it has some theoretical base, the equations, those equations that or the values that you get by using those equations, they are appreciably accurate. So for gases, at least, since we have the kinetic theory, the values predicted by equations which are based on kinetic theory, they are appreciably accurate. So let us move ahead. Now let us know few theoretical equations. So first is we are going to understand a method that was proposed by Wilke and Lee. So these two authors, they proposed one equation for calculating the diffusion coefficients. Let us understand what is that equation. So this method, it is recommended for mixture of non-polar gases, one non-polar gas and other non-polar gas. Or the method is also useful for mixtures of polar and non-polar gases. That is one polar gas and another non-polar gas. So it is useful for mixtures of non-polar gases or mixtures of polar with non-polar gases. So for diffusion of A in a binary mixture of A and B, these authors, Wilke and Lee, they proposed this equation for finding the diffusion coefficient. The equation is DAB is equal to 10 to the power minus 4 into 1.084 minus 0.249 into under root of 1 upon MA plus 1 upon MB into T raised to 3 by 2 into under root of 1 upon MA plus 1 upon MB, the whole thing divided by P into RAB square into function of K into T by epsilon AB. I will tell you what are the terms involved. So if you look at this equation, DAB is depending on MA and MB, that is nature of the component. DAB is depending on temperature and DAB is also depending on pressure. Now let us know what are the terms involved in this equation. So according to this method, for diffusion of A in a binary mixture of A and B, DAB is given by this equation. DAB is equal to 10 to the power minus 4 into 1.084 minus 0.249 into under root of 1 upon MA plus 1 upon MB into T raised to 3 by 2 into under root of 1 upon MA plus 1 upon MB divided by P into RAB square into function of K T by epsilon AB. Now what are the terms involved? Let us understand. So DAB is the diffusion coefficient, as you know. You will be getting it in meters square per second. Then T is absolute temperature in Kelvin. MA and MB, these are molecular weights of E and B respectively. P is the total pressure in Newton per meter square. RAB is the molecular separation between E and B molecules, and it is given in nanometers. I will shortly tell you what is the equation for getting RAB. Then epsilon AB is energy of molecular attraction between the molecules of E and B. Again, we have one equation for getting epsilon AB. So some of the terms I have listed over here. Now let us move ahead. Then K in this equation is the Boltzmann's constant. K is the Boltzmann's constant. Then the function of K into T by epsilon AB, we call that as collision functions. Okay, so these are the terms that are involved in the equation. Let us move ahead. Okay, and now you can get RAB by using this equation. RAB is RA plus RB upon 2. And how to get RA? RA can be obtained by using this equation. RA is equal to 1.18 into VA raised to 1 by 3. And similarly, RB can be obtained in this way. 1.18 into VB raised to 1 by 3. In this case, VA and VB, these are molar volumes of liquid A and liquid B, respectively at their normal boiling points. So VA and VB, these are molar volumes of A and B when they are liquids at their normal boiling point. So in this way, by using these two equations, you can get RA and RB. And once you know RA and RB, you can get RAB by using this equation. Then epsilon AB, you can calculate it from this equation. Epsilon AB is equal to under root of epsilon A into epsilon B. So again, epsilon A can be obtained from this equation. Epsilon A by K is equal to 1.21 into TA, and epsilon B by K is equal to 1.21 into TB. So in this case, K is the Boltzmann's constant and TA and TB, these are the normal boiling points of A and B respectively. So in this way, from epsilon A and epsilon B, which you get from these equations, you can find out epsilon AB by using this equation. So RAB and epsilon AB, they will be calculated in this way. Now the collision function, which is f of kt by epsilon AB, it is obtained from this ratio kt by epsilon AB. So for that we need to use a semi-log plot which is available in the literature. So by using a semi-log plot between f of kt by epsilon AB and kt upon epsilon AB, from this graph, once you know the value for kt by epsilon AB, you can get the corresponding value for this collision function f of kt by epsilon AB. So for example, on y-axis you have the function values, and on the x-axis you have logarithm of kt by epsilon AB. So a graph like this is available in the literature. So for the given value of kt by epsilon AB, we can find the corresponding value of the function, and then you can use this value for the function in this equation to get the value of DAB. So in this way, you can calculate DAB by using this equation, which is proposed by Wilke and Lee. Okay, so now if you look at this equation, you will come to know that the molecular weights, that is Ma and Mb, these are constants. RAB is also constant. So Ma, Mb and RAB in this equation, they are constant. So therefore, we can say that DAB is directly proportional to T raised to 3 by 2. But if you consider the variation of the function also, because in the function you have temperature, so you will be getting a more correct variation. A more correct variation is obtained if the function is also considered. The collision function is also considered, because in the collision function you have temperature. Then DAB is inversely proportional to pressure from this equation. That is, DAB is proportional to 1 by P, and this is true up to pressures of 1500 kilonewton per meter square. So below 1500 kilonewton per meter square, DAB is inversely proportional to the pressure, or DAB is proportional to 1 by P. So from this equation you get this two useful dependence. DAB is directly proportional to T raised to 3 by 2 if you ignore the function, and if you consider it, you are going to get a more correct variation. And the other relationship is DAB is inversely proportional to the pressure. So I hope this is clear to you. You can also find diffusion coefficient for self-diffusion. That is, when A diffuses in A diffusing in A. So you have self-diffusion, and for self-diffusion, we can find the diffusion coefficient. And how can you do that? You just have to, it can be determined, the diffusion coefficient for self-diffusion, it can be determined by setting B is equal to A in the above equation. So if you make this changes, then you can use this equation even for finding diffusion coefficient for self-diffusion. Now the problem with this equation is not convenient to use, since we have to know the function, the collision function, and for that we need to use the graph that is available in the literature. So that's why this equation is not convenient to use. Now we will know some equations which can be conveniently used for finding diffusion coefficients. Let us move ahead. So another equation that is available in the literature, it was proposed by Fuller and other researchers, Fuller et al. So they proposed a semi-empirical equation which is more convenient to use, and this equation is again it is recommended for mixtures of non-polar gases, and even it is recommended for mixtures of polar and non-polar gases. So for diffusion of A in a binary mixture of A and B, what is the equation? The equation is DAB is equal to 1 into 10 to the power minus 7 into T raised to 1.75 into under root of 1 upon Ma plus 1 upon Mb divided by P into summation VA raised to 1 by 3 plus summation VB raised to 1 by 3 and square of this summation. Now we will know what are the terms involved in this equation. So a semi-empirical equation which is based partly on the experimental data and partly on theoretical concepts. You have a semi-empirical equation means it is partly based on the experimental data and it is partly based on the theoretical concepts. So you have this equation. So in this case, DAB is the diffusion coefficient which will be obtained in meters square per second. Then T is the absolute temperature in Kelvin. MA and MB, these are molecular weights of A and B respectively. P is the total pressure, but in order to use this equation, pressure has to be in atmosphere. Then summation VA is sum of structural volume increments for E. Now in my next video lecture, I will be discussing one numerical. And in that numerical, I will tell you how to get this sum of structural volume increments for E. And similarly, you have summation of VB, which is sum of structural volume increments for B. So in my next video, I will tell you how to get this two quantities. So for time being, you just need to know summation VA is sum of structural volume increments for E and summation VB is sum of structural volume increments for B. Let us move ahead. So the equation for diffusion of A in a binary mixture of A and B, the equation is DAB is equal to 1 into 10 to the power minus 7 T raised to 1.75 into under root of 1 upon MA plus 1 upon MB divided by P into summation of VA raised to 1 by 3 plus summation of VB raised to 1 by 3 and square of this summation. Now in the above equation, what you can see, again molecular weights MA and MB, they are constant, and even VA and VB and hence summation VA and summation VB, they are constant, or summation VA and summation VB, they are constant. So that means according to this equation, DAB is directly proportional to T raised to 1.75 and it is inversely proportional to pressure, that is P. So if you combine these two, you are going to get this relationship. DAB is directly proportional to T raised to 1.75 divided by P. So according to the equation that is proposed by Fuller and others, DAB is directly proportional to T raised to 1.75 and it is inversely proportional to P. Okay, there is another equation or another method for determining the diffusion coefficient, and that method is proposed by Gilliland. This method is based on Stephen-Maxwell hard sphere model. So in this case, the gas molecules are considered to be hard spheres. So the method proposed by Gilliland, it is based on Stephen-Maxwell hard sphere model. So again, for diffusion of A in a binary mixture of A and B, you have this equation according to this method. DAB is equal to 0.0043 into T raised to 1.5 into under root of 1 upon MA plus 1 upon MB divided by P into VA raised to 1 by 3 plus VB raised to 1 by 3 and square of this summation. Now what are the terms involved in this equation? DAB is diffusion coefficient in meters square per second. T is absolute temperature in Kelvin. MA and MB, these are molecular weights of A and B respectively. P is the total pressure, and in this equation it will be used in Newton per meter square. Then VA in this case is molar volume of liquid A at its normal boiling point, and it will be in meter cube per kilomole. Then VB is molar volume of liquid B at its normal boiling point, and again it will have to be used in meter cube per kilomole. So in this way, we have various terms in this equation. The equation, this is proposed by Gilliland. Let us move ahead. Okay, then again the equation proposed by Gilliland, which is for diffusion of A in a binary mixture of A and B. We have this equation DAB is equal to 0.0043 into T raised to 1.5 into under root of 1 upon MA plus 1 upon MB divided by P into VA raised to 1 by 3 plus VB raised to 1 by 3 and square of this summation. Now in this equation, in the above equation, again, if you try to find out constant terms, the molecular weight of A, molecular weight of B, VA and VB, these are constant. So that means according to this equation, DAB is directly proportional to T raised to 1.5 and it is inversely proportional to pressure, that is DAB is proportional to 1 by P. So in combination you have DAB directly proportional to T raised to 1.5 and inversely proportional to P. So this is how DAB depends on temperature and pressure according to the method that is proposed by Gilliland. Okay, then we have a method that is proposed by Chen and Othmer. So these two authors, they proposed a semi-empirical method. Then for diffusion of E in a binary mixture of E and B, you can find out the diffusion coefficient from this equation. DAB is equal to 0.01498 into T raised to 1.81 into under root of 1 upon MA plus 1 upon MB divided by P into TCA into PCA and the product raised to 0.1405 into VCA raised to 0.4 plus VCB raised to 0.4 and square of this summation. Now what are the terms involved in this equation? Let us know. DAB is the diffusion coefficient. You are going to get it in centimeters square per second if you use the system of units that I am going to tell you. T is the absolute temperature in Kelvin. MA and MB, these are molecular weights of A and B respectively. P is the total pressure and you have to use it in atmosphere. Then TCA is critical temperature of E in Kelvin. TCB is critical temperature of B in Kelvin. VCA is critical molar volume of E in centimeter cube per gram mole, and VCB is critical molar volume of B in centimeter cube per gram mole. So if you use VCA and VCB in centimeter cube per gram mole, you are going to get DAB in centimeter square per second. P, of course, you will have to use it in atmosphere. So this is the equation that is proposed by Chen and Othmer, which is again based on this is a semi-empirical equation. Let us move ahead. So in the above equation, if you look at this equation, MA, MB, TCA, TCB, VCA and VCB, all these are constant. So that means according to this equation, DAB is proportional to T raised to 1.81 and it is inversely proportional to P, or DAB is proportional to 1 by P. And if you combine these two equations, you have DAB proportional to T raised to 1.81 divided by P. So according to the equation proposed by Chen and Othmer, DAB depends on temperature and pressure in this way. So with this, I will end my discussion for this video lecture. In this video lecture, I have told you about equations, important equations for predicting diffusion coefficients in gases that are available in literature. In my next video, I will be solving few numericals. In my next video, I will be solving one numerical where you will learn how to use this equations. And in coming few videos, I will be solving numericals that are based on estimation of diffusion coefficients for gases. For now, let me end the discussion. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. As I said, in my next video lecture, I will discuss one numerical example which will demonstrate the calculation of diffusion coefficients. A diffusion coefficient in gases by using one of the equations that I have discussed in today's video lecture. So for now, have a nice day. Bye bye, and hope to see you soon in my next video lecture.